Hi everybody, this is a supplemental video for our in-class acid-base activity on Thursday. The first thing I wanted you to do was to identify the acid and the conjugate base for each specific reaction. So let's take the first one for example. If I look at the starting material underlined in red and look at it on the right hand side, it looks like it gained a proton. So this must be my base if it's gaining a proton. And then on the right hand side, after it's gained the proton, it must be the conjugate acid. So I'll go ahead and plug that in. And that means correspondingly, this hydronium ion on the left hand side must be our acid. And on the right hand side, this would be our conjugate base. Okay, so now we've identified our acids and bases for step one. Now we need to estimate the pKa of each of our two acids. So let's try to find the pKa for the acid on the left hand side. So hydronium ion. If you go and look at the chart, it tells you the acid and the corresponding pKa. Looks like it's negative 1.74. So let's plug that in. So all right, pKa equals negative 1.74 here. And then we need to find the pKa of our conjugate acid, which in this case is protonated acetone. So let's go look at the chart. Protonated acetone is actually right above it. It is negative 2.9. So let's plug that in. We'll say conjugate acid has a pKa of negative 2.9. Let me slide this up. And there we go. So now the question is, well, which acid is stronger in solution? Is the acid on the left going to be stronger, or is the acid on the right going to be stronger? In this case, the acid on the right has a lower pKa. It's more negative. So it's going to push the reaction in the opposite direction. So for example, I'd say it's going to push really hard going that way. The other acid's weaker. So maybe it's only going to push a little that way. So this would be the most appropriate equilibrium arrows we could draw for this reaction. If you did switch it and say, well, if this is the conjugate acid, isn't that really acting as the true acid in solution? That would be fine too. Just make sure you have everything flip-flop. All right, let's go to the next one. Next one, we're looking at one of these protons getting removed over here. That means that this must be our acid. And on the right-hand side, this must be our conjugate base. I'll just write conj B. And that means correspondingly, if the molecule on the left is our acid, hydroxide must be our base, and this must be our conjugate acid. Okay, so let's look at the pKa for this acid on the left-hand side. If we go through the chart and we try to look for it, it looks like it's down here at about 9.0. So we'll go ahead and plug that in. pKa is going to be equal to 9.0. And then our conjugate acid over here is water. And if you remember from class, water is typically thought to have a pKa of about 15.7. So we'll go ahead and plug that in. Okay, so let me erase these. Got pKa of 15.7. All right, so now when we're comparing our acid pKa to our conjugate acid, and it appears that this compound on the left is the stronger acid because it has a lower pKa. It's going to push the reaction towards the right-hand side. And so our equilibrium is going to be off balance and favor the right-hand side products rather than the left-hand side compounds. All right, in the next one, we're looking for the pKa of acetone. And we know that this is our acid of interest because it looks like it's losing a proton. So I'll go ahead and just label this as my acid and this is my conjugate base. All right, if we look at the pKa of acetone on the next page, looks like it's about 19.2, so we'll plug that in. pKa equals 19.2. And then over here, this must be our base because it's taking the proton, which means over here that this is our conjugate acid. So let's look up the conjugate acid pKa for ammonia. And if we look at ammonia, it's got a pKa of about 38. So let's plug that in. All right, so it looks like our acid on the left-hand side is much stronger than the conjugate acid. So it's going to push the equilibrium to the opposite side, and the equilibrium is going to favor the compounds on the right over the compounds on the left. All right, so last but not least, let's do the final one. This one's a bit harder. So if we look at this one, the main question is the compound on the left our acid, or is the compound on the right our acid? Well, let's consider both situations. So down here, I'll draw one possible option. So maybe in this one, this is going to act as our base. And then this compound is going to act as our acid. So let's just do this for the sake of argument. And I'm not going to worry about equilibrium arrows right now. So if that's our base on the left, that means it's going to gain a proton. And our conjugate acid would look like this, with lone pairs. And our conjugate base would have an oxygen with a negative charge, right? All right, so this is our conjugate base. And then this would be our conjugate acid. Let's compare that to the flip-flop version. So let's say we do the same reaction. However, this time, we're going to treat this compound as our acid. And then this compound over here as our base. All right, that means we could consider our acid. It will lose its proton. So that means our conjugate base would be this one. And our conjugate acid, in this case, would be ethanol with an extra proton. All right, and if you remember in class, I said anytime you're comparing two relative acids to one another, always look at the stability of the conjugate base. In this case, we've got to ask ourselves which of these two conjugate bases is more stable, therefore which reaction is more favorable. And if we look at the one on top, it's got a negative charge on oxygen. The one on the bottom has a negative charge on oxygen. So we're kind of tied. If you remember from the cardio rules, first thing we look at is charge. We're tied, they're both -1. Second thing we look at is the atom. We're still tied, both charges are on the oxygen. And then next we look for resonance. Conjugate base B, the one on, or the conjugate base underneath, has resonance where the one on top doesn't. So this one's going to be more stable. Which means that this reaction on the bottom is going to be far more likely to occur than the one shown on the top. So let's go ahead and plug in our products and then try to make sense of our equilibrium arrows. So we'll have a negative charge here. This is called the phenoxide anion. And then over here we'll have protonated ethanol. Those will be our conjugate acids and bases. I'm just going to erase everything up here just for the sake of clarity. And then down below we want to determine our pKa's for our conjugate acid and our original acid, and then determine which ones got the lower pKa. Whoops. So let me move all of this up. Okay. If we look at the pKa of phenol, we can go to the chart and say, all right, pKa of phenol is about 9.9. Let's plug that in. So pKa equals 9.9. If we look at the pKa of our conjugate acid, it's protonated ethanol. And if you look at the chart, we're looking for something where we've got an oxygen with a positive charge and 2 protons coming off of it. The closest one I'm seeing would be something like this. It's not perfect though, so if you ever can't find something, you can always look at a more detailed pKa table. So let's pull up the Evans pKa table. And if we look at the Evans pKa table, we're looking for a protonated alcohol or just a protonated species. So we've got protonated species on the far right-hand column. And then if you go down, we're trying to find the closest match possible. This one down here, if you look at it, it's an oxygen between two methyl groups. So this would be a protonated ether. We're not a protonated ether. We're looking for a protonated alcohol. This one down here looks pretty dang close. This is protonated methanol, and that's got a pKa of negative 2.2. So it's probably closer to negative 2.2 than that negative 1.7 value, but still pretty close. So let's go ahead and plug that in. So we've got that answer in. And if we look at this, this conjugate acid is clearly the stronger acid, which makes sense because it's going to push the equilibrium that way, a little bit that way, and this matches the equilibrium arrows that were given to you. So it's showing you exactly what we would expect. All right, so we're not quite done yet. If you go through and you read the directions on this, it said draw arrows representing the proton transfer. So let's go ahead and do that. And it's important to remember that the base is going to grab a proton, but we always show our electrons coming from our base to that proton. And students often forget that you need to break this covalent bond and dump electrons onto that oxygen. So we can show it going from left to right, or we can show it going right to left. So maybe we do the reverse reaction and show this grabbing its proton back and putting it on the oxygen. All right, same thing for the one below. The base is going to reach over, grab that proton, break that covalent bond. It's always a 2-arrow process. And then conversely, we could do the opposite and have the conjugate base steal its proton back from our conjugate acid. Next one, same idea. Base is going to steal a proton from our acid, and our conjugate base theoretically could steal it back. This is always a dynamic reaction. And then on the bottom, we said that this compound's our acid, this one's our base. So in this case, our base is going to reach over, grab our proton off of our acid, kick electrons over, and then the reverse reaction is pretty similar, where we can kick electrons up onto that oxygen. All right, I hope that makes sense. You're more than welcome to email me if you have any questions over the weekend. We will have our quiz on Monday, so make sure you're comfortable with arrow pushing and predicting relative equilibrium positions. All right, good luck studying.